Okay. Right. Well, we get started. So, that's not right. Oh, I've moved it too far to the left. Okay. You got the question? Yeah. Let me remember. Is the first one the force between two 1 kilogram masses 1 meter apart? Yeah. Okay. So you're using your formula F equals G M1 M2 over R squared. G is G, M is 1, M is 1, R is 1. So that's 6.67 times 10 to the minus 11 newtons. Probably got that okay. And what's the difference in number 2?
What is the gravitational force between two equal masses of 10 to the power 6 kg 1 meter apart?
So that's equal G times 10 to the 12. Is that 66.7? Okay. Number 3. What's happening now?
What is the velocity of the Earth as it orbits the Sun?
Okay. So you have V, is this just 3, not like 3 part 1?
Yeah.
Yeah. V equals omega R, which equals 2 pi over T R, which equals 2 pi R over T, which is 2 pi, and then the time is 365 times 24 times 3600. What's the radius of the orbit? The distance the Earth is to the Sun? Should be on the top somewhere.
Distance between Earth and the Sun is 1.5 times
10 to the power of?
11.
Okay. Do you have this calculated? Yeah, that'd be great. 2988. Yeah. So that's 29.9 kilometers per second, yeah? Easy peasy? Right, what's number 4?
How far does a spaceship need to be from Earth's hook so that the total force acting on it from both the Earth and the Moon is 0?
Okay, so what you have here is the Earth, here is the Moon, and here is your spaceship. So it's going to be pulled left to the Earth and it's going to be pulled right to the Moon. And at some point these two will be balanced. This point is actually called L1, I think. Anyways, that's not important. So we need to figure out where that is. So the force to the left will be G, mass of the Earth, mass of the spaceship, over, and what we'll do is we'll call this distance here to here, and X. Wow, look who showed up. And then this distance here to here, we know this distance, I'll call it big R. The distance between the Earth and the Moon. I'll probably give you that in the question, right? So that's over X squared, and that's equal to G, mass of the Moon, times mass of the spaceship, all over R minus X squared. Yeah? Cancel, 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 cross multiply. Mass of the Earth times or minus x squared equals mass of the Moon times x squared. Square root everything. Square root, cancel, square root, cancel. So root mass of the Earth or minus root mass of the Earth x equals root mass of the Moon x. So that means root mass of the Earth or equals root mass of the Moon x plus root mass of the Earth x. So that means x would be or times root mass of the Earth over root mass of the Moon plus root mass of the Earth. So Siva, what does it say in the question the distance between the Earth and the Moon is? 385,000 kilometers. And what's the mass of the Earth?
5.97.
Yeah.
Times 10 to the power 24.
Like that. And then what is the mass of the Moon?
7.34 times 10 to the 22.
Okay. If you can hit those numbers in, then we can have our distance figured out when you're ready.
So 3465
3, 4, 6, 5,
71477.
71477. Okay, so what's that? That's 304. That's kilometers. 1, 2, 3. 347,000 kilometers. Got that? Yeah? Yeah? Okay. What's number 5? Math this time, since Siva gave me 1 to 4. You know, Chow took my book home yesterday. So I don't have a book now. What's number 5, Matt?
What is the gravitational field strength due to the Earth on a plane which is 10 km above the surface of the Earth?
Okay, so here you are. You're 10 kilometers above the Earth and you want your G, which is gm over r squared. So that's equal to 6.67. What's the mass of the Earth? 5.97 times 10 to the 24. And what's the radius of the Earth?
6,371 kilometers.
6,371 kilometers. So that many meters. Plus 10 more kilometers. So this, I'm guessing the answer would be something like, I don't know, 9.6. Something like this. A little less than 9.8. What did you get?
9.79.
Oh, okay, not as small as I thought. 9.79 newtons per kilogram. Okay, is there more question? Oh, who the heck is calling me? Do I want to answer? I don't think I want to answer. Alright, what's next now? Oh, sorry, you need a minute, Siva? Just let me know when you're ready.
What is the gravitational field strength due to the move on the surface of the Earth?
Right, okay. So, there's the Earth. There's you. What is the gravitational field strength due to the moon on the surface of the Earth? So, believe it or not, the Earth is pulling you down, but the moon is also pulling you up. But the strength of that field must be pretty small. Let's calculate what it is. So it's gm over r squared. So that's 6.67 times 10 to the minus 11. Now what's the mass of the moon?
7.34.
Yep.
That's
10 to 22. Okay. Now we have to be careful with the distance. The distance is the distance between the moon and the centre of the Earth minus the radius of the Earth, which puts us here. Yeah? So how far? They're 385, isn't it? 0, 0, 0. Isn't that the distance between the Earth and the moon?
Yeah,
Kilometres? Oh, kilometres, so 0, 0, 0. Minus the radius of the Earth, which is 6,371, 0, 0, 0. Now I'm expecting a very small number here. Do you have it calculated already, Matt? No? Okay, so if you could, yeah, write this down and recalculate.
Distance between the moon and Earth is 36 degrees.
It's usually centre to centre. Unless I say it's surface to surface in the question. Do I just say distance between the Earth and the moon?
Distance between the moon and the Earth.
I'm not clear. I think that usually means centre to centre. I'll double check. Three point 4.2. It's 2.5. 10 to the minus 5. Ah, small. Smaller than I thought. Newtons per kilogram. So 34.2 micronewtons per kilogram. Sorry, did you say 34.2 or 34.3 if you round off? Okay. Is there more? There's more questions? No. Ready? Oh, okay, thanks, Eva. Yeah.
A rocket is fired into orbit that is slightly above the Earth, the surface of the Earth, and is braking through the atmosphere. The engine is about to be cut off. How fast does the rocket need to be traveling at so it can escape the bullet?
Okay, so this is what you want, guys. You want... This rocket here has two types of energy. It has kinetic and potential. Ugh. And potential. If you want it to be free, how much energy should it have here?
So it's not square.
Oh yeah, thank you. Keep forgetting. If you want it to be free, how much energy does it need to have? Just imagine it's not really moving. It's just sitting out here a far distance away, not moving. It's free from the Earth. So it has no kinetic and no potential. So in other words, it has no energy here. So the energy at the beginning, which is this, needs to equal 0 to be free. Yeah? So that means a half mv squared equals gmm over r. Cancel, cancel. V squared equals 2gm over r. Yeah. So v is the square root of that. So that's square root 2 times 6.67 times 10 to the minus 11 times 5.97 times 10 to the 24, is it, the mass of the Earth?
Yeah.
And then over the radius, 6371. Oh. So this should be a pretty big number. It's pretty fast.
11180.
11180. Okay. So that is 11.2 kilometers per second. Is that the end of that worksheet? There's more! My goodness. How many questions did I give you?
8.
Okay. What a jerk. Alright. 8.
A proton and an electron are sent to the power of minus 10 meter apart. By what order of magnitude is the electrostatic force greater than the gravitational force?
Okay, so what's happening here, there's a force pulling the two of them together, caused by the fact that this is plus and this is minus. But there's also a gravity force as well. This has a mass and this has a mass. Now, the force due to Coulomb's law is bigger than the force due to Newton's law. How much bigger? Let's see. So the force due to Coulomb's law is 1 over 4 pi epsilon 0 charge of proton, charge of electron over the distance. The or is, we said, 10 to the minus 10, or squared. So that's E squared over 4 pi epsilon 0 or squared. The force due to Newton's law is G, mass of the proton, mass of the electron over or squared. Now, the force of Coulomb will be much bigger than the force due to Newton. How many times bigger? We can divide to figure out how much bigger. So for example, if the answer was 2, then it means this is twice as big as this. If it was 10, it means it's 10 times bigger. So let's calculate. This would be E squared over 4 pi epsilon 0 or squared over G M P M E over or squared. So the or squareds cancel, and you're left with E squared over 4 pi epsilon 0 G mass of the proton, mass of the electron. So this is on your calculator. This is constant 1 and this is constant 3 if you have this on your calculator. Or you could just type the numbers in. Matt, you have these constants on your calculator, don't you? So maybe it'd be easier for you to type it in. Yeah, it should be. Yeah, what you get?
Very big.
Yeah, yeah, it should be very big, yeah.
2.26
Yeah.
times 10 to the power 39.
Mm-hmm. That sounds reasonable. Let's see. Let me check on Google here. Yeah, so just checking here on this website, it says for the electron and the proton, the gravitational force is 39 orders of magnitude. That's this 39 here. Weaker than the electric force. So that's correct. You're talking about 39 orders of magnitude. That's a lot. Just to be clear, 1 order of magnitude is 10 to the 1, which is 10 times bigger. 2 orders of magnitude, 100 times bigger. 3, 1,000. 6, 1,000,000. 9, 1,000,000,000. 12, 1,000,000,000,000. We still have to get up to 39. You know? So it means that gravity is extremely weak. Extremely weak force. So weak that you don't even notice it when you're looking at protons and electrons. It's just ridiculously small. You couldn't possibly measure it. It's so small. Impossible. Okay. That was the last one of that worksheet? Oh, sorry. What was my answer for number 7? What was the last one?
11.2 K/s.
Oh, yeah. Alright, shall we look at Kepler now? Did you get to try that last night?